Good morning to all. Today we are going to discuss about interrupts and interrupt service routines. In the previous session we have discussed the stack structure of 8086. So in today's session we are going to study about interrupts. So first of all, what is an interrupt? Interrupt, by the name you can able to understand, it is stopping your program temporarily. So an interrupt can either be a hardware generated call, like an externally derived from a hardware signal, some wrongly pressed switch, wrongly pressed button unknowingly, or software generated call internally derived from the execution of an instruction or by some other internal event. So on a whole, we can tell that interrupt can be either from a hardware interrupt or we can call software interrupt. So what is this hardware and software interrupt? Hardware interrupt is nothing but if suddenly there goes a power while processing your program, it is a hardware generated call. Or if any button is being pressed unknowingly in the keyboard, that is hardware generated call. Or the second one is software generated call, which is we are calling some loop or some instruction where it stops the current execution and goes to that loop and goes for execution. This is an interrupt. So when an interrupt occurs, the CPU is interrupted. CPU will stop its execution and the CPU will attend to the interrupt and then carries on. After completion of the interrupt program, then it carries on where it left off. So types of interrupts, as I told you, hardware, software. Hardware, an external signal is applied to the NMI input pin or the INT-R pin. NMI input is nothing but non-maskable interrupt, and INT-R, which can be called as interrupt request. So these two pins are my hardware interrupt pins present in the pin configuration of 8086. Non-maskable interrupt, so you can't be able to mask it, the interrupt which occurred, and the interrupt which require the attention, we will be requesting that by using INT-R pin. Coming to the software type of interrupt, we have an int instruction. In some programs we will be writing this int instruction followed by some operand, so which tells what type of error it is, what type of interrupt it is, and it execute that instruction, such as, for example, divide by 0. So we have software interrupt as int instruction. So whenever we are calling an int instruction in the program, it is called as software interrupt. It executes that interrupt service routine. So when an interrupt is requested, so what the interrupt service routine is, or I can call as interrupt service procedure is, right? So you can see here the mainline program is executing step by step. Suddenly an interrupt occurs, it stops the execution here and comes to the interrupt service procedure. So what it does, The CPU finishes executing current instruction. Yeah, it finishes the executing current instruction and stops. Then it pushes the flag register to the onto the stack. It pushes the flag register onto the stack. It disables the interrupt request input, INTR. So interrupt request will be 0 by clearing the IF in the flag register and also clear the trap flag in the flag register. So what it does, it disables the interrupt request pin by clearing the IF flag as well as TF. IF is nothing but interrupt flag. So we'll be clearing that interrupt flag and trap flag and pushes the current CS contents onto the stack. So whatever the code segment current is will be top of the stack. Pushes the current IP contents onto the stack instruction pointer and does an indirect far jump to the start of the interrupt service routines. Interrupt service routines. So whenever an interrupt is requested, the current execution will be stopped after finishing the execution of current instruction, pushes the flag register onto the stack, clears the IF, clears the TF, push the code current execution of the code segment content onto the stack and pushes the IP content onto the stack, which will fetch the ISR address into the stack and it will do the interrupt service routine first completed, again coming back it will pop the IP, nothing but popping the IP, popping the CS and popping the flags. Then again coming back, which will be fetching the IP address, which will start execution of the current program. So in this manner, when an interrupt is being occurred, so it will stop the current execution, it will push the flags, it will clear the flags and push the content of CS, nothing but where my interrupt service routine is, push the IP address and fetch ISR address. Executing is done. Then after completing of interrupt, it comes back to the pop IP, again pop CS, again pop flags, then coming back to the current execution or the actual program execution part. This is how interrupts is being handled in 8086. Clear? Normal procedure. So only difference in normal procedure is we will be using a return at the end of a procedure, whereas ISRs will be using an IRET instruction instead of RET. So after your ISR has been executed, there will be an instruction called interrupt return instruction. So after that instruction, it goes to the POPs IP, POP CS and flag registers. Then ISRs can be interrupted. This is how the interrupts will be handled by 8086. So very important one, interrupt vector table. So how these interrupts are being put in a table for storing the various addresses of a interrupt service routines. So in 8086, first 1 kilobytes of memory, 50H2 003FFH is set aside as a table for storing the starting addresses of interrupt service procedures routines. Since 4 bytes are required to store CS and IP values for each ISP, the table can hold the starting addresses of up to 256 interrupts. The starting address of an ISP is called interrupt vector. The starting address of the ISP is called as interrupt vector or interrupt pointer, and the table is referred as interrupt vector table, or we can call as interrupt pointer table. Each double word interrupt vector is identified by a number from 0 to 255, as it is 256 interrupts. Intel call this number the type of interrupt. So we have the numbers from 0 to 256 interrupts. You can see here. So this is how the vector table will be. It is starting from 4 bytes will be for CS. So 0 000 4H, type 0, then point type 1, type 2, type 3, type 4, like that. We have type 255 pointers, which are 256 interrupts are being present in your interrupt vector table. So lowest to 5 interrupts are dedicated to the specific interrupts such as divide by 0, single step, non-maskable interrupt, interrupt caused by an instruction, and overflow interrupt. So first 5 interrupt are divide by 0 error. If any divide by 0 error, it is an interrupt. Single step interrupt, non-maskable interrupt, interrupt caused by an instruction, and overflow interrupt. Then from interrupts 5 to 31 are reserved by Intel for more complex processes. The upper 224 interrupts from 32 to type 255 are available for users to use for hardware or software interrupts. The upper 244 interrupts from 32 to 255 type are available for users to use hardware or software interrupts. The vector for each interrupt requires 4 memory locations. Therefore, when the 8086 responds to a particular type of interrupt, it automatically multiplies the type by 4. As we require 4 memory locations, the type will be multiplied with the 4 to produce the desired address in the table to get the starting address of the ISP. Getting a point here? So as each interrupt or each type requires 4 memory locations, so the type will be multiplied by 4 in order to know the exactly address of the type of the interrupt service routines. So an 8086 interrupt can come from any of the 3 sources, which are hardware interrupt, software interrupt, and interrupt caused by some error condition, like divided by 0. So from 32 to 255 we can use hardware and software. First 5 you can get for an interrupt by some error condition. So what actions will be taken by 8086 when an interrupt occurs means, at the end of each instruction cycle, 8086 checks to see if any interrupts have been requested. If an interrupt has been requested, 8086 responds to the interrupt by stepping through the following series of major actions, like we have seen in the stack. Nothing but decrement the pointer IP by 2 and pushes the flag register onto the stack. Disables interrupt request by clearing interrupt flag and trapped flag. It decrements SP by 2 and pushes the current CS register to the stack. It decrements SP by again by 2, which pushes the current IP contents of the stack. Nothing but when an interrupt occurs, it stops the execution. What we have discussed, it takes the same steps. So it does an indirect far jump to the start of the procedure that is written to respond to the interrupt. So as we all know, type 0 interrupt is a divide by 0 interrupt which may occur in your flags, and the address starts from 4 zeros H. Type 1 single, nothing but system will stop after it executes each instruction and wait for further direction from the user. Single step execution, single step interrupt. Type 2 interrupt is NMI. Whenever NMI is enabled, we will get a step 2, which is non-maskable interrupt. because this interrupt cannot be disabled intentionally or accidentally. For example, if pressure sensor in a large system boiler can be connected to NMI input, if the pressure sensor goes a certain preset limit, the sensor will send an interrupt signal to the 8086. Type 3, we have inter3 function, inter3 instruction, which is type 3 breakpoint interrupt. So it breaks and goes to the end. Type 4, into 4H, which results in the output has been stored in the correct register or not. Overflow interrupt, type 4. So this is about interrupts and interrupt service routines. So we have 256 interrupts types, and once interrupt has been requested, it stops the current instruction, current execution of the instruction, and goes to the ISR. So it pushes the flag register onto the stack, pushes the make your TF and IF as 0, push CS, push IP, complete the condition, complete the ISP, there will be a IRECT instruction which will be returning back to the interrupted program. So this is how the 8086 will be handling the interrupts. Thank you.